be, so hopefully we can finish our conjugate gradient. Okay, so our first midterm will be based on part of the coding, and which involves reading public available package, like PyTorch manual. Okay, so and answer questions. You guys will see in homework too. Okay, so we'll be reading like documentation of a software package, and we'll be asked to translate, the coding to a mathematical formula, something like that. And so now let's recall the convergence result. So under the setting, under our setting, which is okay. So this is our function we would like to minimize. So Q is a symmetric, positive, definite matrix. Okay. So we know that. So X star. We know that there exists a unique local minimizer. Unique local minimizer means this local minimizer is global minimizer. So there exists a unique local minimizer that so this equals 0 because the gradient of this quadratic function in n dimension is qx star subtract b, and this is, we plug in this is b subtract b, this is 0. So we learned that our gradient descent algorithm, regardless of where we start, okay? So regardless where we start, so if we move in the direction of, negative gradient with step size alpha, and if alpha is less than 2 divided by the maximum eigenvalue of Q, and then we know that we have the following rate of convergence. That is our next iteration. Error will be less than or equal to kappa subtract 1, kappa plus 1. So kappa subtract 1 divided by kappa plus 1 times the error at previous iteration. So this is like a review. And where kappa is a condition number, kappa is the lambda maximum of Q divided by lambda minimum. So let me add a line. Okay, so if this, we know that this algorithm converges. Okay. So furthermore, if alpha k equals 2 divided by lambda minimum plus lambda maximum, we can achieve this like the fastest rate of convergence for the gradient descent algorithm. Okay.
Excuse me. Can you please remove the chair? The chair.
Oh. Okay. Thank you.
Yeah.
Okay. So, I mean, for mathematics, this is a theorem, you know. But as a practitioner, what we ought to do is we decode information from the theorem, like what we need to improve, okay, from the method. Think about this. To get the fastest convergence, in this simple algorithm, what we need is, we need alpha k is less than, so the step size has to be small enough. And how small is, we need to know the information of the eigenvalue of Q. Okay, so unfortunately, for a very big matrix Q, so if Q is big, for example, we're solving a linear regression problem with like 10,000 features. So then this Q is like a 10,000 by 10,000 matrix, the normal matrix for this linear regression. So then it turns out, okay, because there are other algorithms which I will teach next semester, like another graduate class, most about these modern linear algebra algorithms for machine learning. So to solve the eigenvalue of the matrix, okay, to get the eigenvalue of the matrix, the common way is to do power iteration and an accelerated power iteration called Arnoldi or Lanczos. But all of those to get this lambda maximum and lambda minimum is actually the difficulty, the computational difficulty is equivalent to get the minimum itself. All right. So what it tells us is, I mean, this is like still unrealistic. Why? Because we still have to try. We still have to try. For example, we set alpha k to be 0.01. Okay, we find it doesn't converge. What it tells us is it's not less than this. Okay, but to find this eigenvalue itself, it's as difficult as the original minimization problem. So this theorem is not that, I would say, feasible. So then here comes another. That is, we do the line search I introduced earlier. Okay, and we derived how a line search should be. That is, we find an optimal alpha k at each iteration k. Okay. So what we do is this alpha k is equal to the argmin. So I'll explain in a moment. Let's define argmin here. So what does argmin mean? So if x star is a minimizer of min x of a function, then the notation, so this is equivalent of saying x star is the argument of, so argument just means, so argument returns the location, so where this minimum is achieved, while min is like this function value. So argmin just means it returns the variable or the parameter that makes this function minimum. All right. So what does this? So looking for looking for this just means we find this is the equivalent of we look for an alpha k such that, okay, such that we look for the minimum of this. All right. So if we use a 1D diagram to illustrate this, if in 1D we have a quadratic function, okay, so if we have 1D, we have a quadratic function, and we're currently at here, we follow the negative gradient, we follow the next negative gradient, which will move to the negative direction of x-axis. What happens with line search is we find the minimum function value along the negative gradient direction. We find alpha, so we move in the negative gradient, the alpha, such that along this negative gradient, the function achieves the minimum. So in line search, if we do gradient descent, our next iterate may be here. Then we have to do gradient descent again. But if we do line search, we will directly reach this minimum in one iteration because we minimize along this direction. Okay? But this is in 1D. In 1D, line search will achieve the minimum in one iteration, but in multi-dimension, things will get much, much more complicated. So that's the motivation we introduced the conjugate gradient method. Okay.
So in line search, we are searching the whole thing.
So we'll search. So it's like so this gentleman's question is in line search. What does exactly line search mean? Maybe this is a question. The line search is this is a negative gradient direction.
Yeah.
Okay. So we search this line. So basically we move in this direction. Okay. And we search the function value such that in this direction, our function value achieves the minimum value. Okay. So if we search this direction, is like we evaluated all possible function value, but without actually doing the actual evaluation. Okay. So we kind of find all possible function value will get the smallest in that direction. Okay. In 1D, because in 1D, we literally have one direction. Okay. So in 1D, if we're here, we search in this direction. Okay. So we'll hit the minimum for sure. So this will be our alpha k if our xk is here. Okay? Maybe divided by the negative gradient.
So it doesn't matter that we assume like our gradient is negative or positive in our line search? Because like sometimes it's just like from this way, sometimes from this way. Like...
Okay, so in 1D, the negative, so in 1D, so for example, this is, so let's use this example. For example, this may be this function, okay? At this point, the negative gradient will be positive. Y prime is 2x minus 1. So if x minus 1, so negative gradient is 2 times 1 minus x. Okay. So if our xk is here, the negative gradient will be positive. Okay, we're in the positive direction, and we search in the positive direction, we'll hit the minimum for sure. Because line search is we search all possible steps that we reach the minimum in that direction. So this is what line search tells us. So we search in this direction, And once we hit the minimum in this direction, we stop. Okay. Similarly, if our xk is here, so if this is 1, then this thing is bigger than 1. Negative gradient will be negative. So the negative gradient will be in that direction. And we search along this direction, then we will sure hit this local minimizer. Okay. All right. So this has a name. So this is called a steepest descent. So we'll analyze the steepest descent, but in a different norm. Before we do that, we need to have an identity. So first, let's recall the Taylor expansion. Let's first write down the Taylor expansion in our original notes. Then we'll write down a new formula. So that will be better for all of us. So the Taylor expansion for f is a quadratic function. Okay. So its Taylor expansion somehow is actually itself. So, but we still write it down. So this was a Taylor expansion we had, because f is quadratic. Its Taylor expansion is itself. So a quadratic function Taylor expansion is itself. For example, if we have a function that is quadratic, for example, its Taylor expansion is itself. Okay. So same thing here in multi-dimension. Its Taylor expansion is itself. Okay. All right. So now what we need to now, what we do is we simply let this to be x, okay? And then what happens is alpha d is x subtract x star. Okay. So we can write this as alpha d. We distribute this alpha here and alpha here. Now what's happening is we have f of x subtract f of x star equals alpha, so equals this guy, okay, so which is gradient of x star transpose multiply with x subtract x star plus the nicest thing about this Taylor expansion is we know at x star this is 0. So we have actually a gauge of so we establish like this is a function values difference between the best one and arbitrary one, okay? And this is how far away this x is from our x star. Okay, and this we know, the Hessian of a quadratic function, because Q is symmetric, so it's Q itself. We have a 1/2 factor. So now we have an identity. So we have an identity. That is F subtract F evaluated at the local minimizer is 1/2 X subtract X star transpose Q X subtract X star. Or if we like to use the inner product formula we introduced last time, is Q X subtract X star times, or inner product with X subtract X star. Okay. And there's another nice property. There's another nice property about this inner product, is because Q is positive. Okay. Q is positive. It's actually this is well defined. Okay. So you see why? So basically what happens is we can define the square root of Q. So how do we define the square root of Q is, so now we do this eigen decomposition again. Okay. This is a diagonal matrix. Okay. And all of its eigenvalues are positive. So what we can do is we can take square root of this diagonal matrix. So U is a unitary matrix. This is just a diagonalization of this positive, symmetric positive definite matrix. So we have, this is, we take square root of this diagonal matrix. We have this. Okay. And because diagonal matrix is transpose is just itself, so we have this is, this is lambda square root times U transpose lambda square root U. So this can be defined. So this is defined as our square root of Q. So square root of Q transpose times square root of Q, we get back to Q. Okay, because Q is positive, we have this square root. All right. So we can write something like this. And furthermore, we define this as what we call the inner norm, or the Q norm, or matrix norm associated with a matrix. Okay. So this is definition. So the definition of Q norm. So L2 norm, let's recall, the L2 norm is defined by X inner product with itself. So if we have a symmetric positive definite matrix Q, then its Q norm is something like this, because it's Q's square root is well defined. Okay? Only if Q is SPD, we can do that. So now if we look at this identity, we'll get something very nice. So first of all, alpha k is chosen such that this is like our next iterate. So this is our current iterate. And this is our next iterate. So we want to derive a formula such that our next iterate, we want to derive an error equation that is similar to what we had. So the error equation for gradient descent, if we recall, is, so for gradient descent, it's this. Okay. So for our line search, okay, so we have something slightly different because we want to take advantage of this identity. So now if we look at so now if we plug in the next iterate to that identity, so let's write down this identity. So this identity is now we look at our steepest descent for the line search method. That is, alpha k is chosen that the function value is minimum. And that just means this x of k plus 1's iteration is x k iteration subtract our alpha k gradient evaluate xk. So now we take advantage of this again. Yeah, let me know. Don't erase this. Use a new line. We add an artificial term. This is 0. Give me a second. Yeah, we can use actually that. Yeah, we don't have to do what I did in the notes. Don't think so. Yeah, I need to update my notes, but yeah, let's do this. Okay, so it's not that difficult. Sorry. So this is nothing but we simply do this. We do this again. We don't have to. So this is our x. K plus 1. Subtract x star q norm square. And we add this gradient at x star again. Okay. So this is xk subtract alpha k gradient of x star subtract x star plus alpha k gradient evaluated at x star q naught. So we use the same. Argument we had for the gradient descent. We will have this as x case iterate subtract x star subtract alpha k gradient of evaluate at x k subtract gradient evaluate at x star q naught square. So same thing. Then we will have this is 1/2 I subtract alpha kq because gradient of f is qx, so gradient of f is qx subtract b. So this term becomes subtract alpha k qx k subtract qx star. And b got cancelled. And so we have the same. I subtract alpha kq. But this time it's in q naught. So this time it's in Q norm, and if we do Q norm, what happens is we do the Cauchy-Schwarz inequality again, okay? But this time we find, oh, it's slightly different, okay? Because if we have Q norm, if we expand this, okay, this is I subtract, so we use that, use the identity over there. This is Q half x kth iterate subtract x star Q half x kth iterate subtract x star. this is definition of Q norm. This is this should be square because we have a square here. Okay. Now what happens is we treat this one, okay, as a vector. So this is a vector, this is a vector in Rn. We multiply the square root of Q with another vector in Rn, okay? So what happens is this one is less than or equal to, okay, 1/2 the maximum y in Rn. Y is not 0. Y transpose y, y transpose I subtract alpha q square. And we have this. So this is our Q norm. This is our Q norm.
Question.
Yes.
Should I have a Q subscript? Because if it's the Q,
So yeah, I'm about to write this. So the first term, this is the maximum eigenvalue, so it's the same thing. So by definition, this is the maximum eigenvalue of I subtract alpha kq square, and this is our Q norm. So what happens is, now what we have, okay, so now let's look at our line search. So we have our identity. Okay. So we want to leave a space here. What our line search method does is we add a minimize alpha on both left and the right of this inequality. So to make this inequality much sharper.
We minimize it, but it's still greater than 0.
Yeah, we can, for example, on both sides of the inequality, they have alpha. Think about this. this xk plus 1 is alpha, and this equals, so this identity is, this equals this, right? So now let's like comb up our logic and just thread of thought here. So this is the minimum value, okay? This is where our next iterate will be. So this is always greater than or equal to that. This is the minimizer, okay? So this is the minimum value. So this quantity is always positive. So we minimize this quantity using our step size. So we can, step size is like our parameter. So we can change the step size. We make this minimum, but this is in turn that, okay? And this is less than that. So what's happening is if we minimize this, which is, I already erased it, but we find an alpha so that this is minimized, then we have this guaranteed bound. Okay. And then from gradient descent algorithm, this is from gradient descent algorithm. So from gradient descent algorithm analysis, convergence analysis, this thing, we analyzed this. Okay. Took 1/2 in front. So this is less than or equal to 1/2 we wrote right there, okay? So this is rho alpha, and where rho alpha is 1/2 maximum of these two values, that is 1 subtract alpha lambda maximum of Q, and 1 subtract alpha lambda minimum of Q. Okay. And we know that it's minimum value. So if we take the minimum value, so we have, okay, so we take this minimum alpha, then it becomes, so the minimum alpha is let me continue here. Okay. So it equals minimum alpha 1/2 maximum of these two values. All right. So recall the diagram we drew last time. The minimum value of alpha of the maximum of this two. So the maximum function is here. Okay, this is a maximum function such that it converges. And the minimum alpha of this maximum function is achieved here. So this is our alpha star. And this quantity, when we take the minimum, when we plug in this minimum value, it is kappa subtract 1 over kappa plus 1, where kappa is the condition number of Q. Okay. So now here comes our theorem of line search. So what we did is, so now let's, once we take the minimum of alpha on both sides, we have the minimum alpha 1/2, sorry, just 1/2. So if we remove everywhere 1/2, so we have our theorem. This is what we have derived. Sorry, we have this square, square, and then we have square. So if we remove square everywhere, we will have this is less than minimum of alpha greater than 1 of rho alpha. Okay. All right. So this is rho alpha square. So if we remove square everywhere, we know that this will be kappa subtract 1 divided by kappa plus 1. So now here comes our theorem of line search. Okay. So that is, so same setting with GD, okay? So we have our function. So let me omit the same setting. So same setting with gradient descent convergence, but except our alpha k is chosen such that, as we do a line search, such that the function value is a minimum along this line. If we do this line search. If we do the line search, then we have this guaranteed convergence. So then our convergence is in the Q norm. And this is our convergence, where kappa is a conditional. What is the morality of this theorem is, if we do line search, we do not have to know. So if we do this line search, which we know the solution, so if we recall, we have derived the solution as follows. The solution is G gradient at kth iteration times gradient itself, and then divided by G at kth iteration transpose Q times GK. Where GK equals the gradient kth iteration. And this is q times xk subtract phi. This is called the residual. So what's the idea behind the theorem is no need, even the bound has eigenvalue because the condition number depends on eigenvalue, but the algorithm itself, no need to know, okay, lambda max of q or lambda minimum of q, okay, to guarantee the convergence. If we do a line search, we don't need to know the eigenvalues of Q. The line search, okay, is also the idea, one of the driving idea for quasi-Newton method, which is the state of art, first order optimization algorithm. So let's continue our introduction coding lecture. So for example, this is our notebook. So once you open up, by open notebook, upload, and choose file. Choose the file we just downloaded from Canvas, so we can open it. So I'll upload more introductory notebook to Canvas, like to teach us, for example, how to use keyboard shortcut, those sort of thing. And if we want to clear everything, what we can do is, there is no shortcut. Okay, so let me demonstrate using shortcut. So what we can do is, we can hit a shortcut called Control and Shift and P. So this will be in the shortcut instruction typed in in our canvas. So this is called Command Palette. Okay. What we can do is we can clear. So if we type CL, so it auto completes all the possible options we can do. So we can click clear all output. So then all output gets cleared. And now we can run this again. So we see there is no output now. So it says connected. Okay. So it's connected. All right. And now we import NumPy again. And then we import PyTorch again. So for example, we check still PyTorch 2.0. Okay. So for example, this is how we initialize a matrix in NumPy. Okay. So it's formatted in a way such that it looks like a matrix, but we don't have to do this. So for example, we can perfectly do this keyboard is weird. Okay, we can perfectly do this. So for example, the first bracket just means, okay, it's a first row. This is the second row. This is the third line. And the print command is we print the representation of this vector, or this matrix, or this tensor, whatever we would like to call it. So if we do print, it prints something like this for the first, for this command, and you print x's type, which is integer 64. So we use 64-bit of memory to store each number in this matrix. Okay. So this is this matrix. And the same thing, so if we have plain NumPy or even MATLAB, so for example, in MATLAB we initialize, so let me type the MATLAB initialization here. So for example, this is actually the same. Same thing as we put in MATLAB, but what happens is we just do, so this is MATLAB initialization. So what we would do in MATLAB. Okay. So this is what we would do in MATLAB to initialize the same matrix here in NumPy. In MATLAB we do this. Okay. And in NumPy we do this. In PyTorch we do the same thing, except we change the NumPy array command. So NumPy dot array command to torch dot tensor command. Okay. Let me do this. And we hit Control and Enter again. We run this cell. So we'll see this is torch tensor, and the first line print the torch tensor. The second line prints its type. It's called torch float 32. So this is a standard default PyTorch data type. That is, we use float, which uses 32-bit of memory to store each number in this matrix. Okay. So there are some typical command in NumPy. So for example, if we run these, we'll see this generates a number from 0 to 10, but non-inclusive. So another command is called arange. So a range right here. So it's just array range. So it's the same thing. If we do that, we get the same. So this is not a range. Okay, so it's a and range. And then we can take the sum. We get 45. And if we use dir, it prints. Okay. So all possible functions associated with x. Okay. So for example, we have this many functions, and we can scroll this. And this is the same thing as, same as np sum x. But this is object oriented. Why? Why this is good? Why this line of command is much better than this? The reason is because this is package independent. Okay? So for each package, for example, NumPy has implemented a sum function for the same variable. So for example, now we have the torch tensor, okay, which is still a matrix or a vector or a tensor. We can call the same sum. We don't have to know what variable this method is. So this is a powerful dynamic typing object-oriented language Python is we don't have to know. This is a PyTorch tensor. This is a NumPy array. We can call the same function sum on this variable. Okay, so we get 45. All right. So then we have various functions. So you guys can try what this do. For example, the clamp The clip, sorry, is a famous ReLU function. Okay. So if we do this, so NumPy array, we do clip, we see that all the negative value becomes 0. Okay. So if we have X tensor, which we try the same thing, okay. So we copy this. We change this to torch tensor, and if we clip the same thing, oh sorry, this is xt equal that. So if we clamp the same thing, so it's using another method, I guess. I think it has clamp. Then every negative value is gone. Okay. So for example, what this does, so if we dissect this, let me move this upward. So what happens is, so for example, we can add 1 to this tensor. This tensor is this. So for example, we can add 1 to this tensor. And so every number is added by 1. So for example, this becomes 0.7, this becomes 0.9. And but x, this tensor doesn't like change. It's still the original tensor right here. Okay, so we can try this. So if we do this, we find, oh, if we add -5 to it, every number became negative. And if we do the same ReLU operation, it becomes everything is 0. But if we only add 3, -3, which will minus 3 here, so the first 3 entry will be negative, and the last one will still be positive. So we'll get, okay, so the last one will be 1, but everything negative will become 0. So now next is if we have this underscore here. So if our function has an underscore, it's what is called in-place operation. That is, originally we add 1, this tensor is still the original value we initialized it. But now if we add 1, it becomes this, okay. Then xt, the original tensor we evaluated, is added 1. Okay. So this is another special, like I would say that we need to pay attention for PyTorch. Okay. So here are some common functions of PyTorch that we can play with. So next is we have these functions.
Excuse me. As long as we don't like write print, it's like, you know, it has in memory like the previous, like the first, like the way that we define it at the first place, right?
Okay.
Like that xt. Like you do multiple things, but it doesn't change until you print xt. And it's like, or is it?
So to answer this question, it's not the print. It's not the print changes it. It's this add underscore changes it.
Okay.
So what print does is it prints its, so every like a Python object has what we called a representation. Okay. So what print does is display this representation. Okay, so this representation is this, and then it displays that. So the print command it's pretty much like MATLAB display function. Okay, so so let me so print doesn't change things. So similar to MATLAB display.
So the one right above the print statement, that one, you didn't type print, but it still like outputted something.
Yeah, so okay, so this is a nice thing about the notebook is, so if we we perform certain functions, certain operations, so this window, so the window under the cell will display the result. Okay, so this is one of the nice thing about this interactive programming and using notebook. And then, okay, so here's a thing we like to go through. So for example, we have a matrix. So now we initialize a matrix. And we have a vector. So even though it's a row vector, but by default, when we perform the matrix vector multiplication, this row vector is being treated like a column. For example, A dot x is this matrix A times this x. So we will get 2, 1. It's actually, even though it's displayed as a row vector, but it's A times this x being treated like a column. But it displays like in rows. Okay. So very similar things. So if we change this A and X to PyTorch tensors, okay, and in PyTorch, the matrix vector multiplication is this MM method. For example, this is the same thing as A times X. Okay. So matrix vector multiplication. Okay, MAT2 must be a matrix. Wow, 2.0 addresses this. Okay. All right. So then what happens is, so we have this runtime error, right? You can do this, search Stack Overflow, but the thing is, MAT2 must be a matrix. So what does it mean is right now it's a vector. So we have to reshape it into a matrix. So a matrix is like has 2 dimensions. Okay. So for example, we can reshape it into a matrix. So this reshape command. So right here. So this is one way to make this vector into a matrix. Okay. So this dot reshape, this command makes xt a matrix. So for example, if we do this, okay, so we'll see there's an extra bracket here. If we check the difference, okay. So this is only 1 dimension, and right now this is like a 2 by 1 vector. Okay, so this is PyTorch's, I don't know, like people tries to be consistent, I guess. So now it's shape. So originally, so now if we print, okay, xt shape, and we print, so this guy's shape, so it has a new line. That's interesting. So if we print this guy's shape, we'll see that they're different. The first one is 2, nothing. The second one is 2, 1. Okay, so this is like this is torch size. This isn't torch size. So this is a 2, which means it's a vector, and this is 2, 1, which means it's a matrix. So now what we can do is now we get our matrix multiplication. So next is I want to go through is a Boolean indexing. Okay. So I want to do NumPy. Let me delete this. So next is a Boolean indexing. For example, we generate a random. So this is a random matrix of size 2 rows and 5 columns, okay, and with normal distribution, so standard normal. So if we do that, we get a 2 by 5 matrix with standard normal like random variable, mean 0, and standard deviation 1. Okay. So if we clamp it, we find the same thing. The negative value is gone. Okay. Negative value is gone. So what we can have here is we can have a Boolean array So for example, this is negative, 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 negative. Then at every negative, if we check whether it's positive, we'll get a Boolean matrix. Boolean just means true or false. We'll get a false here and true here. So what we can do, so now this is the same thing. This is the same function as clamp. So now if we can do this, so let me add a code cell above. So if we do this, this gives us the indices where every value is less than or equal to 0. And if we do this, we'll return all these values. So let's try it. You see? So this gives us all the negative values. Okay. So then these line of code setting every negative value to 0. So this is using Boolean indexing. It's a recommended way to do vectorized programming. Okay. And we can see it has the same effect as we're using this clamp command. Okay. All right, so let me delete this. So that's it for today. So I'll upload this one to Canvas.
Hi. Do you want to exchange information to Word document?
Yeah, sure. So, 5. Can I just call if you don't
Yeah.
mind? Yeah, I got it. Okay. Yeah, this is my name.
Oh, okay. Like that's easier. I will text you.
So, what do you need?
Like I haven't looked at the homework yet, but just like
Yeah,
whenever
sure.
like I start